Okay, and our last topic about the nucleus and how the nucleus can change through nuclear type events is radioactive decay. And in order to really get into this topic, you have to remember that every atom is composed of protons and neutrons. And those protons and neutrons are in set amounts. And some atoms have more neutrons than others. But what we don't know yet is that there is a perfect ratio of protons to neutrons. And when that perfect ratio is out of balance, we now have atoms that are unstable. And so this video is going to get into how do those unstable atoms behave? What is their response? Okay, so there are 3 vocab words that are going to be used throughout this video. And the first is spontaneous, so something that happens all by itself. Isotope, which we're familiar with at this point, so atoms of the same element with different numbers of neutrons. And our last one is frequency. Frequency is going to refer to the vibration of a wave. So the vibration of a sound wave, perhaps, or the vibration of a radio wave, or maybe a light wave. Okay, so topic question number 1, what is radioactivity? Well, radioactivity is that spontaneous release of particles or energy from an atom. So when an atom is unstable, it's going to spontaneously give its particles or energy away that's causing the instability. Kind of like a sneeze. You know it's coming and it's just going to come out. At this point, it's important to just remember that we have those strong forces that hold an atom together. And when those strong forces are weakened, now we're going to have this spontaneous release of whatever energy is causing that instability. So what atoms are unstable? I mentioned that there was that perfect ratio of protons to neutrons, but let's figure out more. So in all atoms, the positively charged protons in the nucleus repel each other. And we've looked at that before due to magnetic repulsion. Another way we said that in class was that positives repel and opposites attract. So in really big atoms with lots of protons, this repulsion causes instability. Imagine this atom here of polonium has 84 protons. That's a lot of positive charge. So how is the positive charge here balanced out? How is this atom ever going to be stable? Well, it achieves some sort of stability by balancing it with some neutrons. And there has to be enough neutrons within that nucleus that all those positive charges are separate from each other. Well, if the glue of the nucleus is that force holding everything together, the bigger the atom, the weaker that force becomes. And so very large atoms on the periodic table are going to have weaker, strong nuclear forces. Their nucleus is more likely to just break apart spontaneously. Okay, so now question 3. Which elements have these radioactive isotopes? Which elements are the ones that have a greater ability to just sort of fall apart and be unstable? Well, all isotopes of technetium, so number 43, promethium, are all considered radioactive, and all elements with an atomic number greater than number 83. So I mentioned there was that perfect ratio of protons to neutrons to make stable atoms. Well, anything greater than number 83 on the periodic table, they don't really have that perfect ratio anymore, and so they're unstable, and they're going to go through radioactive decay more quickly. Okay, so what are these types of radioactive decay? I've said the word, but we haven't really gotten into it. Well, there are 2 types of radioactive decay. One of them is alpha decay, the other is beta decay. They both produce something different, they both give off something different, but they both result in a transmutation or change of the nucleus. And again, the end result of radioactive decay is to give off something within the nucleus that is unstable in an attempt to create a more stable environment. Okay, alpha decay is our first topic. And in alpha decay, you have an unstable nucleus that gives off 2 protons and 2 neutrons, which together form a nucleus of helium. So we would have an unstable nucleus that essentially gives a helium away. to be stable. The alpha particle, which is this helium nucleus here, it's slow and it's large and it's fairly low energy. So if we said that there was radioactive decay occurring and an alpha particle was given off, you could actually just hold up a piece of paper and block it. Okay, it's slow, it's low energy, and it's large. Our second type of radioactive decay is beta decay. Beta decay is a little more high energy. If beta decay was occurring, we would have to shield ourselves with a piece of aluminum foil. So in this one, we have a large unstable nucleus, and it's going to give off a neutron. But that neutron is going to quickly convert into a proton, and then a fast-moving electron is the thing that is released from the nucleus. Remember that electrons don't have any mass, and the charge is negative. So let's see how these things change the atom during the reaction. So in alpha decay, the parent isotope is going to spit out that helium nucleus. It's just going to give it away. And the parent decay, which is polonium in this example, is going to now become a daughter isotope, in this case lead. So when polonium lost its 2 protons, it actually became a lighter element. Take a look at these mass numbers. And in alpha decay, the masses will add up to whatever the parent atom was originally. Additionally, the proton values will add up to what it was originally. So overall, we don't have a change in mass and we don't have a change in protons. Everything is still conserved. It just went from something that was unstable to something that was more stable. In beta decay, the neutron in the parent isotope becomes a proton. So we're going to gain a proton, but the mass is going to stay the same. And the reason why is because that neutron converted, and the only thing that was given off was an electron that didn't have any mass. So we're going to change the nucleus from something unstable to something more stable because we're able to convert a neutron to a proton. Okay, so radioactive isotopes can decay, but how long does it take? Well, every radioactive isotope has a different half-life or decay time. The half-life of a radioisotope is the length of time it takes for its radioactivity to fall to half of its original value. One of the applications that you have seen this in, perhaps, is when we talk about carbon dating in fossils. So it's the amount of time it takes for half of that radiation, or it's the amount of time it takes for the radiation within an object or a sample to decrease by half. Okay, so now that we've talked about the 2 forms of radioactive decay, alpha and beta, and you know that there is an input and an output, so what it started with and what it ended with, and a little bit more about how they decay, practice what you've learned in answering the Sum It Up questions.